So there are some interesting second order equations that we can't actually solve exactly, but we'd like to have some information about. Here's a typical one. So this, if you have a pendulum swinging back and forth, right, like this, and to describe the position of the pendulum, you measure the angle that it makes with the vertical like this. You call this angle theta. Then it turns out if you do the physics, then the angle theta obeys this differential equation. Actually, I'm missing a minus sign. This should be minus sine theta. Also, I've neglected some constants that should be here. So there should be some constants involving the mass of the pendulum bob, the length of the rod of the pendulum, and also the strength of gravity. But, ignoring all of those, it doesn't qualitatively change what happens in this situation. This differential equation is extremely nonlinear because of the sine of theta instead of just theta. If the system is near a stable equilibrium, you can use the small angle approximation for sine to get a linear approximation for this equation. But what if you want the full-blown actual equation that has minus sine theta on the right-hand side? What can you do? Well, solving it really isn't going to happen because it's just too complicated. If this were a first-order equation with this on the right-hand side, then it would be separable and we could make some progress, but this is a second-order equation. So what can we do? Well, if you think back to first-order equations, something that we could do for autonomous equations is draw a phase line. We can do something similar for the second-order equation, except it's not going to be a line, because to characterize the state of the system, we need to write down not just what the angle is, but also the rate of change of the angle. Right? You can essentially view this as the space of all initial conditions. And we know for a second order equation, an initial condition is a value for theta and a value for theta prime. So this differential equation takes the form second derivative of theta with respect to time is some function of theta and theta prime. Since t doesn't explicitly appear in this equation, right, that's what makes this autonomous. So we can imagine at every point in this plane, theta is, we can draw little arrows to sort of represent how each coordinate is changing. So at this point, theta is, right, some value here. Theta prime has some value. How fast is theta changing? Well, theta is changing at a rate that we call theta prime, right? And theta prime is this distance. So we can draw a little arrow to indicate that since this distance is positive, theta is increasing. So we can draw an arrow this way. Then we can take this point, put it into this function on the right-hand side, and it will tell us the rate of change of theta prime. And that would be another little arrow. So maybe it would be something like this. To put sort of both of these arrows together into one picture, we could draw the diagonal arrow that goes to the right the appropriate amount and down the appropriate amount. And so we get this blue arrow that tells us if we started at this point in this plane, which is called the phase plane, then the solution that goes through this point would move down and to the right. And you can imagine we could do this for lots and lots of points in the plane, and then solutions would just follow the arrows around. So that's exactly like drawing a phase line for a first order equation, but it's for a second order equation. So it's drawing a phase plane. And there are some nice ways to do this with software. So here I have Sage Math set up to draw some phase planes for us. So if we make the right-hand side of our differential equation minus sine of y, I have to use y instead of theta because that's just the way it's set up. And in the y direction, let's go from minus 10 to plus 10 maybe. Actually, it looks like that's too big. How about minus 5 to plus 5? Okay. So remember how solutions behave in this phase plane is they just follow the arrows around. So if we started, say, up here, this is where theta is 0, so the pendulum would be hanging straight down. But theta prime is positive, so that means the pendulum would be rotating rightwards. So it's hanging straight down but moving to the right. Then following this solution around, it swings to the right. So now theta is positive and theta prime is decreasing, so that means the pendulum is moving to the right and going up. Eventually it reaches some maximum theta value, and then it starts falling back downwards. And indeed, that is what a pendulum does. Once it reaches its maximum height on one side, it falls back to the middle. And here we are again at theta equals 0. But now we're moving in the opposite direction because theta prime is negative. And so then it moves to the pendulum swings to the left. It reaches some maximum negative angle, that is the largest angle to the left, and then it turns around and swings back to the right. So in this region in the phase plane, solutions just sort of go around this loop. And this is just the pendulum swinging back and forth. So what if you put a little more energy into the system? If you push the pendulum really hard, that corresponds to, let me make this a little taller. If you push this pendulum really hard, that corresponds to starting further up in the theta prime axis. So if the pendulum were starting hanging straight down, but you push it really, really hard to the right, then it's just going to sort of move to the right like this. So you can see solutions in this region never really close up and loop around. They just sort of drift rightwards forever. And this, what does drifting rightwards in the phase plane actually mean? Well, in the theta prime direction, we're just sort of moving up and down a little bit vertically. And that means that the angular speed of this pendulum is varying a little bit, but it's always rotating in the same direction, so always spinning clockwise. And since the theta coordinate on these solutions just keeps increasing forever, that means that the pendulum just keeps rotating in the same direction forever. So up here, we've pushed the pendulum so hard that it doesn't swing back and forth. It just sort of swings around and around and around in the same direction. Of course, down below, way down here, there's a similar region, except the pendulum, instead of swinging counterclockwise forever, it swings clockwise forever. It's kind of hard to see the equilibria. The equilibria on this picture are places where the arrow has 0 length. And it turns out there's one hiding right in here. Right? If you start with your theta coordinate being 0 and theta prime being 0, that means the pendulum is hanging straight down and it's not moving, so it's just going to stay there forever. There are more equilibria here and here, so this is where theta is plus or minus pi, and this corresponds to the pendulum being straight up. If the pendulum is perfectly balanced straight up, then it actually won't move at all, although if you give it a slight bump, it will sort of drift down into this region and then start going around. So for many second-order differential equations that you can't solve explicitly, if they're autonomous differential equations, you can at least draw a phase plane and then understand sort of the qualitative behavior of solutions just based on following the arrows around.